All right, we have a question from JAM 2002. JAM 2002, which says the diagram below shows the force extension curve of a piece of wire. The energy stored when the wire is stretched from E to F is dash, and we have the options. Now, as a guide, when solving problems involving curves, curves, let's have this as a guide that if you have a parameter A, if you have that the dimension of parameter A is equivalent to the dimension of a parameter B times that of a parameter C, it then means that for a graph of a curve of BC, for a curve of BC, the area under a graph, the area under the graph B against C is given by A. Yes. That is something we see when we plot a velocity time graph. For a VT graph, velocity time graph, the area under a velocity time graph is given by the distance S. That's because distance S is equivalent to velocity times time. Another example is the graph of force times velocity, which force times velocity, which is equivalent to power. So for a graph of F on the vertical axis against velocity on the horizontal axis, the area under a curve F against V is given by P, which is the power. So likening this now, this is a case of force extension graph. We know that work done or energy is equivalent to force times extension. That is, the dimension of work done is given by the dimension of force times the dimension of E. Of course, we know that in Hooke's law or elastic concepts, that actually W is equals to 1/2 Fe. But since half is a constant, you can assume that the dimension of work is given by the dimension of force times dimension of extension, because of course work is done if force moves a distance. So applying this now, we can infer that to obtain the work done, because the energy stored after being stretched from here to here is something as the work done in doing that, stretching it from here to here. So since this is F force extension curve, so to obtain the work done is given by what? Area under the curve of the part under review. So we are talking about between, sorry, this Q, please, this Q. From E to F, we can complete this as a shape, a full shape. Yes, and of course, we are going to obtain a trapezium. So the area under this place is given as the work done in stretching from here to here. And of course, this is a trapezium. Let's redraw this let's put this here. Let's draw this shape. So we're having good. This is our F. This is our E. This is our F. This is P. And this is Q. And of course, from E to F is given by 0.1 minus 0.05, which will give us 0.05. And from E to P is equals to 0.1 Newton. 0.1 Newton. Y from F to Q is given by what? 0.2 Newton. 0.2 Newton. And of course, the area of a trapezium is given by, so work. The area of this trapezium is given by one over 2 into sum of the parallel sides. These are the parallel sides. So 0.1 plus 0.2 times vertical height, perpendicular height, this perpendicular height from here to the perpendicular height of this times 0.05. So that will give us 1 over 2 into 0.3 times 0.05. And of course, in JAMB exams, it's advisable to work with the decimals, sorry, with the fractions. So to avoid using the calculator, because calculator wastes your time. You can write this as 1 over 2 times 3 over 10 times 5 over 100. Of course, 2 in 2 is 1, 2 in 5 is 2.5. So 3 times 2.5 is 7.5 divided by 10 times 100 is 1000, and 1000 is equal to 10 to the power 3. So divided by 10 raised to the power 3. That will give us 7.5 times 1 over 10 raised to the power 3. And of course, this will give us 7.5 times 10 raised to the power minus 3 joules. That is option C. In our next video, we'll be solving this without making use of the concept of areas under a curve. We'll use the conventional equation for dealing with elastic materials. Until then, thank you.